Hello, and welcome to this presentation related to further transposition of formulae. It is assumed you've seen a previous presentation related to the introduction to transposition of formulae, as that contains underpinning knowledge required for the problems we're going to solve here. Typical formulae we'll be considering are shown here on the slide, and full work solutions are shown to all problems. Here's a presentation overview. We commence with an introduction to the transposition of formulae, also sometimes termed rearranging equations. This introduction states what we mean by transposing a formula or rearranging an equation, and emphasizes the principle of keeping the balance of the equation throughout the transposition process undertaken. We then consider transposing formulae having symbols that are multiplied or divided together. We consider transposing formulae having symbols that are added or subtracted. My ethos with transposition is to show as many examples as possible and try and illustrate the underpinning techniques required using the inverse operation process. For reference, a tabulated list of the various inverse operations we will consider within our solutions is shown within this section. So next we have some tutorial examples. We have to make the symbol shown in the bracket the subject. I've listed the first 4 examples shown here. So given the equation v is equal to u plus at, currently v is the subject of the equation, and we've got to make u the subject of the equation. And similarly, m is equal to u minus kt, m is the subject of the equation, we've got to make again u the subject of the equation. V squared equals u squared plus 2as. V squared is the subject of the equation, we've got to rearrange for s to be the subject, and again considering the same equation, you have to make u the subject of the equation. These examples are worked through in detail. For your reference, here are the approximate start times related to the various sections as shown on this slide, should you want to jump directly to a specific section, but please note all these times are rounded to the nearest minute. Presentation overview continued. The tutorial examples continued. So again, we're transposing the following formulae. Here's example 5 through to 10. Got to consider the equation given and then rearrange it for the symbol shown in the bracket. And for each of the examples, the answers are shown in the square bracket on the right hand side. And here are the approximate start times related to examples 5 through to 10. Again, please note that all times are rounded to the nearest minute. Here are now some tutorial questions for you to attempt at your own pace. Same procedures for the examples. We've got to make the letter or the symbol in the bracket the subject of the stated formula. Question 1 here, v is equal to u plus at, we have to make t the subject of the formula, and again as for the previous slide, the answer is shown in the bracket on the right hand side. This slide shows questions 1 through to question 6. Full work solutions are shown to all the questions. Here are the approximate start times for questions 1 through to 6. Presentation overview continued. And here are the final batch of tutorial questions. Some of these are quite difficult questions, so don't be overly concerned if you're having problems with them. Most technician students will find these difficult. Questions 7 through to 13. Again, we're given the formula and we have to rearrange for the symbol shown in the bracket. Again, answers shown on the right hand side. And here are the approximate start times for questions 7 through to 13. Again, please note all times are rounded to the nearest minute. Note for your reference that within this presentation, a tendency to use the term formula and equation interchangeably, but a formula is shown here on the top of the slide. R is equal to L multiplied by the square root of 1 divided by LC minus F squared divided by 4 pi squared. Currently the subject is R. If we wanted to, we could rearrange to make the subject F, in other words transpose for F. However, an equation such as x plus 3 divided by 4 minus x minus 3 divided by 5 is equal to 2 can be rearranged and solved, in this case for the value of x. So within this presentation we are essentially transposing or rearranging formulae, but the same principles can be applied to rearranging and solving equations. I have added this table of definitions into the presentation for anybody that does want slightly more in-depth understanding of terms of expression, equation and formula, but this is only really for background information. So let's define expression. This is a general term in mathematics for the collection of symbols representing numbers and operations. So here are some examples of numerical expressions. An algebraic expression is one that's formed from constants, coefficients, variables, and operations, such as the plus, the minus, the multiplication and divide. Here are some examples of algebraic expressions: the x cubed minus 2x and the 4a squared minus 27a plus 18. They're all algebraic expressions. Just note for reference, x here is the variable, 4 here term the coefficient, the 18 here is termed the constant. Let's define the term equation. Equation is essentially a statement that two mathematical expressions have the same value. In other words, these two expressions stand for the same number. The example of an equation is 4x is equal to 20. In this equation, we're stating that the 4x and the 20 have the same value. This is only true if x is equal to 5, so x is equal to 5 is termed the solution to the equation. Note for reference that 4y squared minus 27y plus 18 equals to 0 is termed a quadratic equation. And define formula. The formula is an equation stating the relationship between two or more quantities. For example, the volume of a cylinder, symbol V, is calculated from the formula V is equal to pi r squared h, r being the cylinder radius, h being the cylinder height. Note that ax squared plus bx plus c equals to 0 is termed the quadratic formula. So as I say, those definitions are just for your background information. So transposition of formulae. Algebraic transposition relates to the transfer of one quantity or one variable from one side of the equation to the other side of the equation. This process is required when we're manipulating a formula to make a particular variable or symbol the subject of the equation, and we will consider lots of transposition examples within this presentation. One thing that's very important to remember is that the balance of the equation must be maintained in every step of the transposition process. For example, if a quantity is added to one side of the equation, then it must be added to the other side. If a quantity is subtracted from one side of the equation, we must subtract the same quantity from the other side. If one side of the equation is multiplied by a number, so must the other side be multiplied by the same number. If one side of the equation is divided by a number, then so must the other side. If one side of the equation is squared, then we must square the other side of the equation. If one side of the equation is square rooted, then we must square root the other side of the equation. So this principle of balance must be maintained throughout our transposition process. We're going to consider values or symbols that are multiplied together. In other words, they act like a product. What we looked at in the previous presentation was V is equal to IR, which is the formula for Ohm's law, where V is the voltage, I is the current, and R is the resistance. And we wanted to transpose the equation to make R the subject of the equation in the moment V is the subject of the equation. So starting from V is equal to IR, as outlined in the previous presentation, we're going to use inverse operations to rearrange the equation. In the moment I is multiplying the R, so to remove the I from the right hand side and leave us with R, we have to divide by I. But to keep the balance of the equation, we have to divide both sides of the equation by I. Now on the right hand side, the I in the numerator will cancel with the I in the denominator, leave us with a value of 1, and 1 times R is R. So on the right hand side we have now R is equal to, on the left hand side, the V divided by I. So we've got R as the subject, but it's on the right hand side. So for convention we just turn the equation around, put the subject on the left hand side, R is equal to V divided by I. So that's an example of using inverse operations to rearrange the equation, but also keeping the balance of the equation. What we do to one side, we divide it by I, we must do to the other side, divide that by I. Again, another illustration we looked at in the previous presentation was making h the subject of the formula v is equal to pi r squared h. In the moment v is the subject, that's the volume in this case, is equal to pi r squared h, we want to rearrange for h. So from the given equation, v is equal to pi r squared h, because the pi, the r squared and the h are all multiplied together, we can simply divide both sides by pi r squared to leave us with the h. And that's what's happened on the next line. We've divided the right hand side and the left hand side by the pi r squared. So now we can cancel the pi r squared on the top line with the pi r squared on the bottom line to leave us with a value of 1, and 1 times h is h. So on the next line we have h is equal to the v divided by pi r squared on the left hand side. And again, just turn the equation around, h is equal to v divided by pi r squared. So we transpose the equation for h. On this slide we have now symbols divided together, connected as a quotient, in other words, as a fraction. In the first example we've got x is equal to y divided by a, and we've got to make y the subject of the equation. So given the original equation, x is equal to y divided by a. In this particular case I want to make the y the subject of the equation. At the moment a is divided into the y, so the inverse operation is to multiply. On the next line I multiply both sides by a in this case. On the right hand side of the equation now, a divided by a, again gives me 1, and 1 times y is y. So now I have y on the right hand side, that's equal to a multiplied by x on the left hand side. I just simply turn the equation around, so y is equal to ax. On item 4 here we're asked to transpose the equation. M cubed is equal to 4x squared w divided by p. We're asked to transpose it for p. In this particular case p is in the bottom line to begin with, and I need it to be in the top line to be a subject. So the first thing I'm going to do here is multiply both sides by p to get p in the top line. And that's what I've done. On the next line I've multiplied both sides by p. So on the left hand side I have p multiplied by m cubed. On the right hand side that's equal to 4 multiplied by x squared multiplied by w. But of course on the left hand side I don't want p multiplied by m cubed, I just want p. So after p and the m cubed are multiplied together, I now divide both sides by m cubed. So on the next line I have p is equal to 4 multiplied by the x squared multiplied by w, all divided by m cubed. So I've rearranged the equation for p. Now we're going to consider other inverse operations associated with the problems we're going to review. So in the previous examples we had multiplication, its inverse operation was division, and we had division where the inverse operation was multiplication. In the examples we're going to look at, we'll also bring in addition, which inverse operation is subtraction, and of course subtraction, inverse operation addition. And you'll also see we'll be dealing with squares, inverse operation square roots, and square root, inverse operation squares. And we'll also have cube functions, which we will need to cube root, and we'll have cube root functions where the inverse operation is to cube. There's some trigonometric functions such as a sine function, sin, and the inverse operation is arc sine or sine to the minus 1. Stands for the inverse sine function. And for arc sine, the sine to the minus 1, the inverse function is the sine function, and a similar process required for the cosine and the tangent functions with regards to inverse operations. In this example we're asked to transpose the equation given, the m cubed is equal to 4x squared w divided by p, for x. Make x the subject of the equation. So from the original equation, the m cubed equals to 4 multiplied by x squared multiplied by w divided by p. I want to make x the subject, so I need to remove the p from both sides. At the moment the p is dividing into the x term, so I'm going to multiply both sides by p. On the next line I have p multiplied by the m cubed is equal to 4 multiplied by the x squared multiplied by w. But I'm trying to find x, so I need to now remove the 4 and the w from the right hand side. So I'm going to divide both sides by the 4w, which is what's been done here. So I end up with p multiplied by the m cubed divided by 4w, and that's equal to x squared. But I don't want x squared as a subject, I simply want x. Using my inverse operation to square, I will now square root the right hand side of the equation, which means of course I must square root the left hand side of the equation to keep the balance. Turning the equation round, x is equal to the square root of pm cubed divided by 4w. So that's an illustration where we use 3 different types of inverse operation to find the subject x. Here's some examples where the symbols in the formulae are added or subtracted. In item 6 here, we're asked to transpose the formula x equal to 2y minus 6 for y. In this particular case, what I'm going to do is remove the negative 6 from the right hand side and bring that across to the left hand side. So using my inverse operations, I'm going to add 6 to both sides of the equation. So on the left hand side I get x plus 6, and that's now equal to 2y. So on the right hand side I now have 2y, but the question wants me to have y as the subject, not 2y, so I now need to remove the 2 from the right hand side. The 2 is multiplying the y, so the inverse operation is divide. So I'm now going to divide both sides of the equation by 2, and that's what's happened on the next line. I've divided both sides by 2. The 2 cancels on the right hand side, but appears on the denominator on the left hand side. Just turn the equation round, y is equal to x plus 6 divided by 2. In item 7 here, we're asked to transpose the formula P is equal to f plus mu times n, that's a Greek symbol there, for n. So given the equation, P is equal to f plus the mu times n. I'm asked to make n the subject of the equation, so the first thing I'm going to do is remove the f from the right hand side. Don't forget there's a positive in front of the f here, so to remove it I'm going to subtract f from both sides of the equation. So on the next line I now get p minus f on the left hand side, and that's equal to the mu multiplied by n on the right hand side. I'm trying to make capital N the subject, so the mu is multiplying the n, so now I need to divide both sides by mu, and on the next line I've divided both sides by mu, and again just turn the equation round, n is equal to p minus f divided by mu. The final few examples show us formulae containing brackets. We're asked to transpose the equation y is equal to a plus x divided by b to make x the subject of the equation. In the moment y is the subject of the equation. So given the equation y is equal to a plus the x divided by b, I will start by removing the a from the right hand side. Don't forget that's a positive a here, so to remove it from the right hand side I'm going to subtract a from both sides of the equation. So on the next line I get y minus the a, and that's equal to the x divided by b. I want x to be the subject, so I need to remove the b. The b is dividing the x, so the next line I will multiply both sides by b. Now you need to be careful here, multiplying both sides by b, that means I have b multiplied by y and b multiplied by the negative a. We normally put the y minus a in the brackets and show it in this form. So multiplying both sides by b, I get b multiplied by the y minus a in the bracket. And it's very important you have the bracket there. And that's equal to x. Just simply turn the equation round, x is equal to the b multiplied by in brackets there the y minus a. Another example is we're asked to transpose the equation L is equal to a plus in bracket n minus 1 multiplied by d. I'm going to transpose it for n in this particular case. So given the equation L is equal to a plus in brackets n minus 1 or multiplied by d, the first thing I'm going to do is remove the a from the right hand side. Again that's a positive a here, so I'm going to subtract a from both sides of the equation. So on the left hand side I get L minus a is equal to the n minus 1 multiplied by the d. The n is inside the bracket, so I will need to expand the bracket. What I'm going to do here is simply divide both sides by d, and that effectively removes the bracket. So on the next line, dividing both sides by d, I get the L minus a divided by the d, and that leaves me with the n minus 1 on the right hand side. In this case I'm trying to rearrange the equation to make n the subject, so I need to remove the negative 1 from the right hand side, so I'm going to add 1 to both sides of the equation. So on the next line I simply added 1 to both sides. That's now equal to n. So just turning the equation around, n is equal to the L minus a all divided by d plus 1. So lots of inverse operations then required in the transposition of that equation to make n the subject. This is the kind of situation we will encounter more and more in the examples we're going to review in this presentation. Here are some tutorial examples I'm asked to work through. We're asked to make the letter in the bracket to be the subject of the stated formula. So question 1, given the equation v is equal to u plus at, we've got to rearrange the equation to make u the subject of the equation. At the moment v is the subject. So the first thing I'm going to do is to remove at from the right hand side. We've got a positive at, so I need to subtract it from both sides. So my next line would be v minus AT, and that's equal to U. I've now got U as the subject of the equation. I'm just going to rewrite the equation with U on the left hand side. And there's my solution. Question 2, I'm given M is equal to U minus KT. I've got to rearrange the equation again to make U the subject. So I need to remove from the right hand side the negative KT. So on the next line we're going to add KT to both sides of the equation. So on the left hand side I will get M plus my KT, adding it to both sides, and that's equal to U. Again, just turn the equation around. U is equal to M plus KT. And again, my transpose form. In question 3, I'm given an equation of motion. V squared equals to U squared plus 2AS. I've got to rearrange the equation to make S the subject in this case. So the first thing I would do is remove the U squared from the right hand side. So I'm going to subtract U squared from both sides. Don't forget it's a positive U squared. So next line, V squared minus U squared is equal to 2AS. Don't forget the 2 is multiplying the A and the A is multiplying the S. So next line I'm going to divide throughout by the 2A. So I will get V squared minus U squared divided by 2A on the left hand side, and dividing the right hand side by 2A, it leaves me with S. Just turn the equation around, so therefore S is equal to V squared minus U squared, all divided by 2A. So the first thing I'm going to do here is to remove the positive 2AS from the right hand side. I'm going to subtract 2AS from both sides. So my next line will be V squared minus the 2AS, and that's equal to U squared. Because I don't want U squared, I just want U. Then I will square root both sides of the equation. So square root in the left hand side, I get V squared minus 2AS. Square root in the right hand side of the equation, I will get the square root of U squared. Obviously the square and the square root cancel each other, so I've basically got U on the right hand side of the equation. So I'm just going to turn the equation around, so therefore U is equal to the square root of V squared minus 2AS. So again, I'm always thinking of inverse operations when I manipulate the equation, and then I'm keeping the balance by whatever I do to one side of the equation, I do to the other side. We have to transpose the following equation stated for the variable shown in the bracket. So question 5, we've got to rearrange the equation for V squared, question 6 for M, etc. The answers are shown on the right hand side in the square brackets. Just note for reference, this formula here, V is equal to the square root of 2e divided by M, can be written as shown up here. I would encourage you to stop the presentation and attempt these questions, but the full work solutions are shown on the following slides.
Tutorial examples. Here's an overview of the solutions for example 5 and example 6. I'll let you review these solutions at your own pace. They state the various steps involved within the transposition process, but for your reference, the following slides work through these solutions in much greater detail.
So given the equation that V is equal to 2e divided by M, and it's all square rooted here. To find V squared, we're simply going to square both sides of the equation. So square in the left hand side, that becomes V squared. Square in the right hand side, that removes the square root. So I end up with 2e divided by M. There's our solution. Question 6 is the same equation, but this time we've got to transpose the equation to make M the subject of the equation. So in this case, as M is under the square root sign, the first thing I need to do is to remove the square root sign. So I'm going to square both sides of the equation. So now V squared is equal to, on the right hand side, that will be 2e divided by M. So now I need to get my M into the top line to be the subject, so I'm going to multiply both sides by M. So V squared multiplied by M is equal to 2e. But I don't want V squared multiplied by M, I simply want the M, so I need to divide both sides by V squared. So my final step here is dividing both sides by V squared. So M is equal to the 2e divided by the V squared. And there's my solution. Tutorial example solutions. Overview of solutions to question 7 and question 8 here. Again, I'll let you review these at your own pace, but the following slides show the solutions in more detail. Question: given x equal to b plus ay squared, I've got to make b the subject here. So given the equation x equals to b plus ay squared, the first thing I would do is subtract ay squared from both sides. So my next line will be x minus ay squared is equal to b, and just turn the equation around. Therefore b is equal to the x minus ay squared. That's our solution. In question 8 I'm given the same equation, but this time I need to rearrange it to make y the subject. So this time I'm going to remove b from the right hand side of the equation. Don't forget that b is a positive value here, so I'm going to subtract b from both sides. So x minus the b is equal to the ay squared. I now need to remove the a from the right hand side of the equation. The a is multiplying the y squared, so I'll divide both sides by a. So x minus b, and notice all divided by a, is equal to y squared. I don't want y squared, of course, I want y, so I need to now square root both sides of the equation. So x minus b, all divided by a, will be square rooted, and that's simply equal to y on the right hand side, square rooting the y squared. So therefore, turning the equation around, y is equal to the square root of x minus the b, all divided by the a. And there's our solution. Tutorial example solutions continued. Solutions to question 9 and question 10 in overview. And again, the following slides contain more detailed work solutions for your reference. Question 9, we're given f multiplied by t is equal to m, and that's multiplied there by the v1 minus u1 in brackets. We've got to make t the subject this time. This is quite straightforward. If I simply divide both sides by f, I will get t as the subject. So dividing both sides by f, t is equal to the m multiplied by the v1 minus u1 in the brackets there, all divided by f. And there's my solution. Question 10, I give the same equation, but this time I need to make m the subject. So I will simply divide both sides by the bracket to leave myself with the m. So on the next line, that's f multiplied by t, all divided by the v1 minus the u1, and that's equal to m. I just simply turn the equation around, and there's my solution. Here are some more tutorial questions for you to engage with. Questions 1 through to 6 on this slide. Again, the subjects you're looking for is in the brackets, and the final answer is on the right hand side in the square bracket. I'd encourage you to stop the presentation and attempt these questions. They're very similar to the kind of questions we looked at on the previous slide. Tutorial questions, commencement of the solutions. Here's the solution for question 1 and question 2. I'll let you review these solutions at your own pace. Tutorial questions, solutions continued. Solutions to question 3 and question 4. Again, I'll let you review these at your own pace. Tutorial questions, solutions continued. Question 5 and question 6. Let you review these at your own time. Tutorial questions continued here. Questions 7 through to 10. Again, we've got to make the letter in the bracket shown below the subject of the stated formula. So for question 7, we've got to make the subject u. For question 8, we've got to make the subject t, etc. The solutions are shown in the square brackets on the right hand side of the slide. Just for your information, question 7 can be written in this form. If that helps you, write on 2 lines, 1 upon u plus 1 upon v equals 1 upon f. Similarly, equation 8 can be written as z is equal to x multiplied by t squared divided by the u minus t squared. Sometimes seeing the equations written on 2 lines is easier than how they're expressed on the 1 line in the question. I would encourage you to start the presentation and attempt these questions, but the work solutions are shown on the following slide. Tutorial questions, solutions continued. Here's the overview of the solution to question 7. The equation is 1 upon u plus 1 upon v is equal to 1 upon f. It's actually quite a complicated solution, and there are various ways of solving this particular problem. I've included a much more detailed worked solution on the following slides, as I know this particular problem can be difficult for some technician students to solve. Let's consider now the solution to question 7. Just going to rewrite the equation on 2 lines. In this particular question, we're trying to make u the subject of the equation. So the first thing I would do in this process is to subtract the 1 upon v from both sides of the equation to leave me with 1 upon u on the left hand side. So my next line, 1 upon u is equal to 1 upon f minus 1 upon v. There are several ways of solving this problem, but I'm going to use fractions on the right hand side. I'm going to find a common denominator for f and v. Now just for a moment I'm going to consider numerical fractions to show you the process involved if we had numbers instead of letters. Sometimes students find the symbols very confusing. Supposing I was given the sum of 1 upon 2 and I'm subtracting from that 1 upon 3. If I was to find a common denominator for 2 and 3, we would find that by multiplying the 2 by the 3. So 2 multiplied by 3, which is 6 of course, is the common denominator. The way I undertake my fractions, I say how many times does 2 divide into 6? It goes 3 times, so 1 times 3 is 3 on the top line. So how many times does 3 divide into 6? It goes 2 times, so I get 1 times 2 on the top line, so that would be take away 2. So in terms of numerical fractions, I would simply get, in this case, 1 upon 6. So that's the process involved with subtracting fractions with numbers. We're going to apply that same process, but using symbols, and it looks much more confusing with the symbols. The first thing we're going to do is try and find a common denominator for f and v. And just as we found a common denominator for 2 and 3 by multiplying together, we're going to multiply together the f and v to get the common denominator. So on the left hand side I still have 1 upon u, but on the right hand side my common denominator for f and v will be f multiplied by v. Now I say to myself, how many times does the f divide into the f multiplied by v? It will go v times, so 1 times v is v. And continuing the process, how many times does v divide into f multiplied by v? It goes f times, so 1 times the f is f, so I'm subtracting the f on the top line. Again, just consider my thinking steps here. If I'm dividing fv by f, then I can clearly see the f's cancel, top and bottom, to give me 1. F divided by f is 1, and 1 times v is equal to v, so I end up with v. So fv divided by f gives me v. Similarly, if I consider fv, but it's now divided by v, I can cancel the v, top and bottom, again cancel to give me 1, and 1 times f is f. So there are my thinking steps to determine the numerator on the right hand side. So in other words, fv divided by f evaluates to v, and 1 times v is v, and similarly fv divided by v evaluates to f, and 1 times f is f. Now I effectively have these common denominators on both sides of the equation. I can simply invert both sides. So on the left hand side, finding the reciprocal of 1 upon u, gives the value of u. On the right hand side, finding the reciprocal of v minus f divided by fv produces fv divided by v minus f. And that's what we're trying to find. That's our solution. It's quite a complicated solution using fractions. There's another way where you can multiply throughout by u, multiply throughout by v, rearrange the equation, but the fractions I think is a preferred approach here. But it does require a basic understanding of numerical fractions. For your reference, there are presentations on solving numerical fractions and also solving algebraic fractions. Viewing them may help your understanding for solving this question 7 shown here. Tutorial questions, solutions continued. Here's an alternative overview of the solution to question 7. Again, we have to transpose to make u the subject of the equation, and we commence with 1 upon u plus 1 upon v is equal to 1 upon f, as given in the question. So with this solution, we firstly multiply throughout by u, shown here.
Next we multiply throughout by v, shown here. Then we subtract u from both sides of the equation. Then we factorise the right hand side of the equation on u. U is the common factor shown here. Next we divide throughout by the bracket v divided by f minus 1, shown here, making the subject on the left hand side of the equation. This is our final solution for u. And as an alternative format, if you multiply the right hand side, both numerator and denominator, by f, we can show that u is equal to vf divided by the bracket v minus f. All that's happened on the final line, I've just shown the bracket in terms of the reciprocal index. So that's an alternative solution for question 7 without using fractions as we did in the previous solution. Tutorial question solutions continued. Here's an overview of the solution to question 8. Again, you can review this solution at your own pace. The following slide walks you through the solution in more detail. Z is equal to xt squared divided by u minus t squared in the bracket. I've just written this formula on 2 lines here for clarity. Notice that we have to rearrange the equation for symbol t, and that t actually occurs twice. We have a t squared term in the numerator and a t squared term in the denominator. So the solution commences by multiplying both sides by the denominator, the u minus t squared, in the bracket. Notice I must have the bracket around the u minus t squared. Next line, I've expanded the left hand side, so expanded the bracket here. Next line, I've added zt squared to both sides of the equation shown here. Then I've factorised on t squared, and I've divided by the bracket x plus z to leave t squared as a subject, and then square rooting both sides allows me to find t as a subject. That's an outline of the solution for question 8, which is slightly complicated because the t term occurs in 2 positions within the formula. Tutorial question, solutions continued. Overview of the solution to question 9. Okay, let you review this at your own pace.
So in question 9, we're asked to transpose the equation to make little f the subject here. So the first thing I would do is multiply both sides by L. So YL is equal to 3 multiplied by big F minus little f in the bracket. My next line, I'm not going to expand the bracket on the right hand side, I'm simply going to divide both sides by 3. So YL divided by 3 is equal to the big F minus the little f, and the bracket has been removed. But I want to make little f the subject. At the moment it's a negative little f. I'm going to add the little f to both sides to make it positive. So YL divided by 3 plus my little f is equal to big F. And to get the little f on its own, I need to subtract the YL upon 3 from both sides of the equation. So little f is equal to the big F minus YL upon 3. And there's my solution.
Tutorial questions, solutions continued. Overview of the solution to question 10 for your reference. The more detailed work solutions shown on the following slides.
Question 10, we're given t is equal to 2 pi multiplied by the square root of L upon G, and we've got to make L the subject of the equation. T is the subject at the moment. If I rewrite the equation slightly like this, it's 2 pi multiplied by the square root of L over G. So the first thing I would do is divide both sides by the 2 pi. So t divided by 2 pi is equal to the square root of L over G. Now I need the L to be the subject under the square root sign, so I need to square both sides now. T upon 2 pi all squared on the left hand side will be equal to the L upon G on the right hand side. I want to make L the subject, so I need to multiply both sides by G. So G multiplied by the T over 2 pi all squared is now equal to L. Turning the equation round then, L is equal to G multiplied by the T upon 2 pi and that's all squared. So that's nothing wrong with that solution, that's fine, but it's not quite the solution in the question because they've squared the bracket. So therefore we can show that L is equal to the G multiplied by T squared divided by 4 pi squared. So that's what's actually shown in the bracket. Or you could write that as GT squared divided by 4 pi squared. And there's our solution. I'm going to leave you with some further tutorial questions here. Again, we're asked to make the letter in the bracket the subject of the stated formula. In question 11, we're given the equation m is equal to mu multiplied by L, mu being a Greek symbol, divided by L plus little r multiplied by C multiplied by big R. We've got to make L the subject of the equation. At the moment, m is the subject of the equation. Be careful here. Notice that the L occurs in two places. Similar problem in question 12. Given an equation, got to make r the subject of the equation. But again, notice that the r occurs twice. That's the r squared on the top line and r squared on the bottom lines. Again, you've got to be careful with your rearrangement. Finally, question 13. We're given an equation to rearrange. We've got to make capital R the subject of the equation. The r does only occur once in the equation. It's actually r squared, but it's tucked under the square root sign. So again, you've got to be careful with the rearrangement used here. Well, the answers are here, are shown on the right hand side of the slide. I would encourage you to stop the presentation and attempt these questions, but the solutions are shown on the following slides for your reference.
Tutorial questions, solutions continued. This is question 11. Here's the overview of the entire solution for your reference. Tutorial question, solutions continued. Question 12, overview of the entire solution. Quite complicated questions these. Tutorial questions, solutions continued. Question 13, overviewed here for your reference. Again, a very complicated problem to solve. Here's the bibliography used to help generate this presentation, which I hope has been of some use to you in developing your transposition skills, and thank you for viewing.